In lesson 9.4, we're going to learn how to calculate a confidence interval for a difference in two proportions. And we're going to use this in situations where we're interested in comparing an athlete's or a team's ability in two different contexts using categorical variables. For example, with a basketball team, we might want to know if they have a higher winning percentage at home versus on the road. And we've actually looked at this question in different ways throughout this course. Or we might want to know whether a field goal kicker makes a lower percentage of field goals after being iced when the opposing coach calls a timeout right before the field goal is attempted. In both of these cases, we want to know the true difference in the two proportions, or the proportion that we calculate in each context. And so to estimate this, we'll calculate a confidence interval for the difference in two proportions. Now, in section 9.2, this was the formula that we used for calculating a confidence interval for one proportion. And you don't need to write this in your notes, but I just kind of wanted to remind you of the general format of this formula because we're going to use something that looks similar to this, but with two different contexts. So remember, we have p hat, which is the percentage that we calculate based on our performance. And then that value we use again underneath the square root. So we do p hat times 1 minus p hat. N is the number of attempts or our sample size. And then, of course, we have this 2 out in front because if we want to be 95% confident, we have to go out 2 standard deviations. So we're going to tweak this formula. And instead of having just p hat, which is for one context, we're going to have 2 different p hats. And so we're going to use subscripts to denote those. So if we want to estimate a 95% confidence interval for the difference in two proportions, instead of just trying to estimate P, we're going to try to estimate P sub A minus P sub B. So P sub A is the proportion of successes in context A, or actually the ability in context A, and P sub B is the ability in context B. And we want to know the difference in those two abilities. So here's what your formula looks like. We have p hat A minus p hat B. So that takes the place of the p hat in the formula that we used in section 9.2 because we're working with 2 different percentages. Then we do plus or minus 2, and we have that big square root. And notice I've left space underneath there with a plus in between because we're going to put 2 different calculations underneath that square root. In the original formula, we did p hat times 1 minus p hat over n. So we're going to do that first, but we're going to use context A. So we have p hat A times 1 minus p hat A over NA. And that's all the numbers that go along with the first context in your problem. Now we're going to repeat that for context B. So even though the formula looks big and complicated with lots of symbols, it's really just a modification on the formula that we used in section 9.2. So let's define our variables. PA and PB represent the true proportion of success or the athlete's ability in each context. P hat A and P hat B represent the observed proportion of successes or the performance in each context. NA and NA represent the number of attempts or the sample size in each context. And I kind of staggered those on the slides just because with all the different symbols, it was a little bit crowded, just so you could read that clearly. As our first example, we're going to look at how much of a home court advantage the Golden State Warriors had in the 2018-19 season. We have some win-loss data presented for you in a way that you've seen many times before in this course. We've organized it into a two-way table. So with that two-way table, we can calculate their overall record for that season. They finished 54-38. We also can do column totals. So we know that they played 41 games at home and 41 games away. And then, of course, we know that they had 82 games total for their season. Now, in part A, they're asking us how much better the Warriors performed when playing home versus away. In other words, for this season, what was their home court advantage? We need to calculate 2 separate winning percentages. So for home games, they won 34 of their 41 home games for a winning percentage of 0.829. For away, they won 20 out of their 41 home games for a winning percentage of 0.488. Now, the difference in those winning percentages then is 0.341, which seems like a pretty significant difference. Saying that they won 34% more of their games at home than they did on the road is a pretty good home court advantage. Now, based on those single value estimates, we're going to calculate a 95% confidence interval for the true difference in their proportion of wins, home versus away. So let's plug the numbers into the formula. So first we do p hat A minus p hat B. So I did 0.829 minus 0.488. So that's the home versus away winning percentages. Then I do plus or minus 2. I'll put my big square root sign there. And then underneath that square root, I'm going to do p hat times 1 minus p hat divided by the sample size, once for the home games, once for the away games. So for home games, their winning percentage was 0.829. This 0.171 I got just by doing 1 minus their winning percentage at home. And you can either simplify that before you plug it into the formula, or you can just write 1 minus 0.829, whichever you're more comfortable with. Their number of games was 41. Now, for road games, we'll repeat that same process. Their winning percentage on the road was 0.488, and they had 41 games. Now, when you do this calculation, you should be able to type all of this into your calculator in one step and hit enter. Store that number, then take your square root, store that number, then multiply it by 2. And then at that point, you're safe to round. But please don't do any rounding in between. Just keep those numbers stored in your calculator and don't round until you get to that step. That leaves us then with a margin of error of 0.195. And the 0.341, of course, is our single value estimate based on the home and away winning percentages. And that's the same value that we calculated in part A. So our interval then works out to be 0.146 to 0.536. Let's interpret that in context. We would say we are 95% confident that the true difference in the Warriors' ability to win at home versus away is between 0.146 and 0.536. Now, in this example, that entire interval is positive, which means that based on this season, it seems like the Warriors definitely have a home court advantage because they're going to win somewhere between 15 and 54% of more games at home than they do on the road. So that's definitely a good home court advantage for them. Let's do an example involving icing the kicker. So from 2009 to 2000 to 2009, that's 10 seasons, kickers in the NFL made 377 out of 488 field goals without a timeout being called, so not iced, and then 157 of 197 when they were iced. We want to know if there's a difference in their performances. And so we're going to calculate the difference in proportion of successful kicks. Now, just to sort of reinforce the symbol notation, I'm going to use that on this example. So here I'm doing p hat sub I, and instead of doing A and B, I'm going to do iced and not iced because in this problem, it just makes a little bit more sense to use those subscripts instead of A and B, but you can use A and B if you prefer. So when they were iced, they made 157 out of 197 kicks, which is 0.797. When they were not iced, they made 377 out of 488, which is 0.773. So notice that in this block of time, the kickers actually did better iced than not iced. And a lot of times coaches will ice the kicker thinking that, the extra time to wait before they make them kick will kind of make them nervous. And then hopefully they'll make less of their kicks. But it doesn't appear that based on this data, that's the case. But anyway, let's calculate a confidence interval and see what happens. First, we'll do the difference, right? That's what question A is asking us for. So the differences in those percentages is 0.024, which is a pretty small difference. But we're going to go ahead and calculate our confidence interval to get kind of our plausible values for what that true difference actually is. All right, so here's the formula with all of the numbers substituted in, and I kind of followed the formula notation a little bit more. Notice here I did like p hat times 1 minus p hat, and I just wrote it like that. So for those of you that prefer seeing it that way, that's the way that I did it in this example. Now notice that this whole calculation right here is for situations where they were iced, right? So that's for the iced kickers. And over here, we have for the ones that were not iced. So those are all your values for subscript N. I would recommend that you pause the video at this point and try that calculation and see if you can come up with the same margin of error that I do, just to make sure that you understand how the formula works. All right, if you calculated that correctly, you get 0.024 plus or minus a margin of error of 0.069. And that gives us an interval from negative 0.045 to positive 0.093. And we've seen situations like this before where the interval goes from negative to positive and includes that value of 0. So, why we have negative values in this case is because that there probably will be some seasons or some blocks of time where the percentage of kicks made when the kicker was iced was lower than not iced. Because remember, when we subtracted, we did iced minus not iced. So, if the kicker makes fewer when they're iced than they did when they're not iced, then you would get a negative value when you subtract. The fact that 0 is in the interval means that there is essentially no difference between a kicker being iced versus not iced. And if icing the kicker really did make a difference, then we would get the entire interval to be negative. Because again, remember we're doing iced versus not iced, or and so the order we're subtracting in is iced versus not iced. So if icing the kicker really did make a difference, then this number over here would always be smaller than the second one, which would mean we would be getting a negative value for the entire interval. And that is not the case. So, based on this data, it doesn't really appear that icing the kicker makes a difference. Please do homework 9.4 in your assignment packet.